So now that we have the unit circle, there's a very important question that we can ask, and that's why? Why do we need to know all this? Why do we need to figure out these specific points on some circle with a radius of 1, and why, and with these degrees here? Why do I care that, oh, hey, if we go 45 degrees across this unit circle, we get this point, which is root 2 over 2 comma root 2 over 2? And that's because the main application of the unit circle doesn't really come from the circle itself, but it comes from when we apply this to right triangles. And so we can see here that for each degree that we have, it's actually from you have this line from the origin and to a point intersecting the circle. And this point here gives us two separate lengths. It gives us a length in the x direction, which is the first coordinate, or the first value within the coordinate point. And it gives us the length in the y direction, and that's the second value. And so from this, we can see here that we have this nice 90-degree angle, giving us this right triangle, in which the hypotenuse is the longest length of this triangle, which is directly opposite of our 90-degree angle. The hypotenuse is a length of 1. And so drawing this out on the side here to make it a bit easier to see, we can have this nice right triangle. In our specific example here, we have a 30-degree angle, and we have a hypotenuse of length 1. And given from the coordinates point, we know that we have this x length of root 3 over 2 and this y length of 1/2. And let me denote that, putting a little square there to denote that that's a 90-degree angle. And so this is the power of the unit circle. It allows us to work with the most important shape, which are triangles. And so generalizing this, we can use the unit circle to work with this right triangle, in which we have this angle in which we'll call alpha, and we have the hypotenuse, this longest side of the triangle, directly across from our right angle, which we'll call h, and we have the side which is the y length, and we have another side which is the x length. However, you may see this and think, well, yeah, this is cool and all, but given from the unit circle, there's not much that we can really work with, because if we're using these values over here, then the hypotenuse is only just destined to be 1. And that's not really too interesting to work with triangles in which we have the hypotenuse length of 1. But this can be extended to really a hypotenuse of any length, really, because if you want to think about it this way, we can use our unit circle, given that this is 1 unit. That's why it's the unit circle. If we want to have a bigger triangle of, say, let's say a length of 3, a visual way of seeing things is that we can break apart this. Actually, let me draw the full triangle first. So we're going to have this right triangle. Of course, this is not to scale because these look almost the same. We'll say that this hypotenuse has a length of 3. And in that case, we're going to break down this triangle here into 3 separate right triangles. Also, I forgot to denote the right angle there. Into 3 separate triangles that can be found on the unit circle, all of length 1 here. And so we can see that we can just add these up. We have length 1, length 1, length 1, all connected with each other to give us this side length of 3. And we can see that when we bring down our points here, this also goes down. And same thing for sliding our sides over here for these smaller triangles to the right. Same goes over here. We can see that we're going to have this this triangle. If we call this triangle, let's say right here, this would be our x1, and then sliding across over here, this is y1. Over here would be x2. Sliding across over here would be y2. Sliding this piece down would be x3, and this piece on the right would be y3. Then you can see that y is just y1 plus y2 plus y3, and x is equal to x1 plus x2 plus x3. But we can already see that all these triangles are the same because we're going to have this starting angle of alpha, and this angle must remain the same throughout these three triangles. And so that means x1 is equal to x2, which is equal to x3. And so x is just equal to 3x1, and y is equal to 3 times y1, in which essentially what we're saying by this is that by having really any right triangle in which we have our angle alpha here, since this would be 3 times 1. Let's give an example for our alpha. Let's make this our 30 degrees that we had before. This is technically 3 times our hypotenuse length of 1. So that means our y is going to be 3 times our y length for our 30 degree triangle, which is 1/2. And our x would be 3 times the 30 degree length in our x, which is root 3 over 2. And this can apply to really any triangle in which you have a hypotenuse, a y, and an x, in which you have this right angle. And so from this, we would then be able to then use our unit circle here and apply it in this sense as we've seen here. And just a note, this doesn't have to be an integer number. You can have a side length of any number, 2.2 or 5.3. It can be anything really. But this is the important part, that we can use this on really any triangle, any right triangle. And so from this, there are certain methods that we can use, of course, using our trigonometric functions that we've used before, our sine, cosine, and tangent, in order to determine missing side lengths of this triangle. And there are 2 ways about memorizing which functions we should use. And so let's see. So given this triangle here, we may need to figure out what cosine of alpha is. May need to figure out what sine of alpha is, and we may also need to figure out what tangent of alpha is. And so there are going to be 2 ways of remembering what these values are equal to in terms of our picture up here. And so the first one is one that you may have heard before, and this is a great mnemonic in which you can pronounce it out. It's called Sohcahtoa, in which you have the beginning letter of S, C, or T being representative of the trigonometric function you're using, so cosine, sine, or tangent. And then you have the other two letters, O and H, A and H, or O and A, the O, A, or OA, in which these are going to be a fraction of O over H, A over H, or O over A, in which what these letters represent are going to be the hypotenuse for the H, the O for the opposite, and the A for the adjacent from our triangle here. So of course our H, our hypotenuse, it never really changes. However, the reason why we have an O and an A here for opposite and adjacent sides of this triangle is because it's relative to our angle alpha that we're looking at, right? Because within the triangle, regardless of where the angle is, the hypotenuse, defined as the longest leg within the triangle, that's never going to change. However, looking at this angle here, we can see that the opposite side, the side directly across from this angle, in this case, if alpha is defined to be on this angle, our opposite is going to be y. And then our adjacent, the side that is not the hypotenuse but is connected with that angle, is going to be x. But I can easily change this up and say, actually, I want to look for this other angle. This other angle I'll call beta. And if I'm looking at this angle, then I'm going to be looking directly across. And looking directly across from beta, I'm going to see that x is actually my opposite now. And y is the side side that is not the hypotenuse but is adjacent to that angle. And so that's our A, that's our adjacent. And so we can see that this changes depending on the angle that you're looking at, and that's something to take note of. And that's why I didn't give these side lengths specific O or A values. I'm just saying that relative to this alpha here, this is the X, this is the Y. And because that's how it looks like on our unit circle as well. And so from here, we can see that this sine applies to the opposite over the hypotenuse, this cosine applies to the adjacent over the hypotenuse, and this t applies to the opposite over the adjacent, in which we can, if we were to write this out, we can say that sine of alpha is equal to opposite over hypotenuse. Hope I'm spelling that right. And then let me move this. Then we can say that cosine, I don't need the extra letters, cosine of alpha is equal to the adjacent over the hypotenuse. Scoot that over. And then for tangent, it's been mentioned before or previously, but if you don't want to worry about treating this as memorizing, you don't have to, because if you just want to remember Sohcahtoa, then that's all you need to know. And of course for tangent, we know that tangent of alpha is defined to be sine of alpha over cosine alpha, in which from our mnemonic, if we just want to go by remembering Sohcahtoa, then we know that sine, I'm just going to use the O's, the A's, and the H's. Sine is opposite over hypotenuse, so O over H, and cosine is A over H, adjacent over hypotenuse. And since we're doing a division of fractions, we would be able to inverse the denominator and then change our division into multiplication. And so this would be opposite over hypotenuse multiplied by hypotenuse over adjacent, in which our values for the hypotenuse are would cancel out because these are the same. And this gives us O, which is the opposite, over the A, which is the adjacent. And that works out completely fine. However, if you just want to go straight from the mnemonic and just remember the whole thing, Sohcahtoa, that toa part is the TOA, and so tangent of alpha would be equal to the opposite over adjacent, and you just go directly from there. And even though you may see this as more work up here, and you may think of it as, oh, well, you still have to kind of memorize that tangent is equal to sine over cosine. You're still going to have to remember that regardless of if you remember the toa part in the Sohcahtoa or not. And so it's basically the difference is, do you want to memorize 3 things, which are the Sohcah and then the definition of this tangent? Or do you remember and do a little bit more work on that part, but you're memorizing less? Or do you want to memorize 4 things, which is Sohcahtoa, and then not have to worry about deriving everything and doing this work on the top? It's really up to you. I prefer less memorization and just kind of deriving things from the bare minimum, because things can get overwhelming easily. But this is method 1. I'll note that down. This is method 1. Sohcahtoa. This is the main method you'll hear about a lot. Sohcahtoa method of remembering your sine, cosine, and tangent in terms of your triangle here. And I'll also just note down here, if we have a triangle and we have this alpha here, then hypotenuse is always going to be the same, but looking directly across, this is our opposite, and then looking directly at the same side that isn't the hypotenuse, this is our adjacent. And if you were to have a different triangle in which your alpha was up here and everything else was the same, hypotenuse would still remain the same, but the opposite would be side length directly across, and now the adjacent is the opposing side. So that's method 1. Method 2 is a bit different, but it's still the same. Essentially, what we're going to do is, we can see here, if we don't really want to worry about remembering these fractions, we can just treat this as a sine onto the hypotenuse in order to get some side length. And so we basically be multiplying the hypotenuse on both sides to essentially move it over to the other side. And that's what method 2 is about. And the reason I'm even showing this in the first place is because this is better in terms of like physics applications. If you take a course on kinematics, this may help you a lot. But I'm going to call this method I'll call it, let's see, trig on hypotenuse. I don't really have any fancy name for it, because that's kind of what we're doing. We're applying a trig function on the hypotenuse. And so essentially the way you go about kind of remembering this method or making sense of it is that, remember from before how we were saying a way to memorize which way the sine and cosine, how they apply in terms of our unit circle. Let me go to it. Up here, like if we were at 45 degrees and coming to this point, if we had cosine of 45 degrees or sine of 45 degrees, I guess this is a bad example because we'd say which one would we use, but they're the same. So let's switch this up. Let's say 60 degrees. If we went at 60 degrees and we say, okay, we have cosine of 60 degrees and sine of 60 degrees, which value do we use? Do we use the x or the y? Remember that what we said is that the mnemonic is that for every point you have the x comma y value. X comes before y in the English alphabet, and what you have cosine represented as C and sine represented as S, and C comes before S in the alphabet, and so this x relates to the cosine and the y relates to the sine here. And so we're going to use this in method 2 in order to help make sense of this. And so I'm just going to point out to remember that you have your x and y point, which relates your sine to your cosine and sine. And so from this, what we're getting at here is we're saying that cosine relates to the x length, and sine relates to the y length. And so for every single triangle, as I've mentioned before, your hypotenuse will always be the same. It's always going to be that longest length. And so given some angle of alpha here, what we can say is, okay, well, if I want the x length of the hypotenuse, in that case, that is given here, I'm just going to want to say, okay, I'm going to start off with this big line here, and I want to say, okay, only get the direction of travel in the x here. And so I can say that, okay, we have this length of h, and I just want to get the x length of that. So it's h times cosine of alpha. And let me put the h in parentheses so that it's easier to see that it's multiplied. Actually, I'll just put h, and that's bad h. Okay, my bad. H times cosine of alpha, and that's going to be equal to your x value in terms of this alpha here. I'm going to say x, but I'm going to also denote that this is actually the adjacent of alpha. Adjacent side. Yeah, the adjacent side of alpha. And similarly, if I look at this h and I say, okay, I want to get the y length of this. So we've gotten the x length here, in which we've started from our starting point, and we've gone only to the right, giving us how far our hypotenuse has gone to the right, but not at all what it's gone in the y direction, or how far it's gone up. I can do the same exact thing, in which I'm basically starting from the length of this hypotenuse. And then if I want to only get the y length, then I'm just going to be looking at the sine of that hypotenuse. It's almost like saying that these trigonometric factors over here are getting basically the x and the y components of this h vector value. And so h, which is the hypotenuse, times sine alpha, that's going to give us y, in which it's important to note that this only works, remember, in this orientation. Saying these x and y values would not work if I have this other angle here and I call it beta, and I change up this angle being beta and beta there. And so because of that, I'm going to denote that this is actually the opposite side of alpha, because I can easily change this up and say, okay, but then I'm going to have this h here and alpha is now here. And if alpha were to be here, and if we want these equations to be exactly the same, then that means x is going to be here and y is going to be here. So it's a bit different. You can how do I want to say this? You can think of this as maybe treating your starting point as where your angle is, and knowing that in your point you write it as x comma y, and so reading it left to right, you must first go along the x, then go along the y. Of course, if we skip like saying that we shouldn't go across the hypotenuse here, we must then go across the x here and then go across the y here. But seeing the angle like this just makes it weird. That's why method 2, I saved it for the second method, not the first. The first is what you'll see most of the time in any classes going over this. But the second method is a little bit better in terms of kind of seeing this in terms of like a physics application. So this, I'll just note to not get tricked. Don't get tricked. And why not get tricked? Make sure x and y are correct. So we have these two methods about going about remembering this, which you have this, you're applying the trig functions on the hypotenuse, and you have the Sohcahtoa method. Of course, for method 2, I skipped it because I don't even remember it in my head, but the tangent of alpha, in this case it would be equal to sine of alpha over cosine alpha. And from here, if what you can really do is just multiply both sides of these equations by 1 over h, so that basically bring over the h's to the other side, and then this will give you your sine and cosine in terms of how it is in method 1, in which you have some value divided by the hypotenuse, and those are the values that you can put into here. So if we really want to go to that value or get that value, we can see h times sine of alpha, that's our y, h times cosine of alpha is our x, in which then we can move the h to the other side and say that sine of alpha is equal to y over h, cosine of alpha is equal to x over h, and then we can substitute these values in. So we have this is y over h, this is x over h, and then we can do the same exact things before, since we are multiplying by fractions. we'll do the keep change flip method, in which our hypotenuse would cancel out, and then we have y over x. So tangent of theta is y over x. There's not really an easy way to derive that, or have this be part of like the memorization of method 2. In method 2, you have to just kind of derive the tangent, because we're kind of using this this mnemonic here, in which we're just relating sine and cosine to x and y. If we do that, then tangent doesn't really have any place for this. But yeah, so we would be able to really apply this to any triangle. And so, given an example, just to kind of see how this works, we can have something along the lines of this angle, in which we'll say this is 60 degrees, and let's just say we have let's go 6 for the hypotenuse here. And so then what we can do is we say, okay, well then, what's this value? What's this value? We'll say that this is A and this is B. So what method can we do? Well, we can, in this case, we can use method 2 here, and say that, okay, if we want to know A, this is like our y here, this is our x. We can say that A is equal to our hypotenuse times, if we want to get the y value, we're going to need sine of alpha, in which for this problem, h is equal to 6, alpha is equal to 60 degrees, and that's all we know. And so this is equal to 6 times sine of 60 degrees. And so now what's sine of 60 degrees? Well, why don't we just look at our unit circle then? Let's go all the way back up. It's right here. And we see that 60 degrees across here. Let me use a different color. Across here would give us this point here, and then sine is going to be the y value, and so this is root 3 over 2, and the x is going to be 1/2. That's going to be important to remember. Right here, and so this is equal to 6 times root 3 over 2, so we can simplify this and say this is 3 times root 3. And so this is our A value. And then for our B value, we can do the same exact thing. H times cosine alpha. This is 6 times cosine of 60 degrees. We saw before that cosine of 60 degrees is 1/2. And then this is just going to be 3. And so now we can fill in these missing values of the triangle and figure out that the triangle itself, it's actually 3 root 3, 6, and 60 degrees. And this is still neat, but it still begs the question of, okay, well, what about actually applying this? Like, it's cool to find missing sides of the triangles, but when does that come in handy? And this is out of scope in terms of just knowing about the unit circle. A lot of stuff in math, you can easily say that about really anything until you actually do find like the application for it. It's important just to keep note of all your math concepts, because you're just building the tools to later apply it. Like, you need to learn to hammer a nail into something before you figure out that you can hammer that nail into something that's a part of something even bigger, or making some machine out of that. you need to first learn the skill and learn the tool before you apply it to some bigger project or some bigger application. So it's completely fine if you don't understand this entirely, but I think it's important to still talk about the application so that you can at least make some sense of it. And so in physics, especially in kinematics, we want to look at maybe like trajectories of some like ball being thrown in the air. And so if you have some person here, and you have him holding the ball here, let's give him a little smiley face. And let's say he just throws this ball. I don't know. We'll say 15 meters per second. He's a strong lad. He's a strong lad. He can throw it pretty far. What we want to then do is figure out, okay, well, what's this trajectory going to look like, right? Because realistically, this is going to keep going, but then gravity bringing it down is going to bring it back down, and it's going to plop somewhere, like somewhere over here. And we might want to say, okay, well, how far is that distance? Well, we can't just know the speed that the ball's thrown at. We're going to also want to know an angle, right? Because if you just throw it straight up, it's not going to go anywhere. If you throw it straight across to the side, it's just going to quickly fall. But let's just say in terms of this problem, in terms of this problem, that he threw this at an angle of 30 degrees to the floor. And so we can see that this 15 meters per second, in terms of a physics application, we call this a vector, but you don't have to know what this is. The important part is that we can just treat this vector as any old line, in which we have this vector. I guess giving the definition, this vector is just basically a something that has a magnitude and a direction, in which the magnitude is like the length. The length, I guess in air quotes, would be 15 right here, and the direction would be this in the upper right fashion here. And this is thrown at 30 degrees to the floor. And the important part about this is that we can say that, okay, well this arrow here, this vector, can be broken down into two parts. The x component, in which if we're saying that the velocity v is equal to 15, we can say that the velocity in the x is equal to whatever this vector pointing to the right is. And if we just go straight up, we can say that the velocity in the y is equal to whatever this component is. We'll give it the units, 15 meters per second. Then what we can do is, hey, we can see, look, we have a right triangle. And so since we have this right triangle here, we can use everything that we've just learned before and figure out, okay, what's the velocity in the x? What's the velocity of the y? And let's just use what we learned so far. We can say, okay, well, we have this 15 meters per second. If we want to figure out what the velocity in the x is, this is going to be the hypotenuse times cosine of 30 degrees, which is going to be 15 times, I believe, 1/2, if I remember my unit circle correctly. I think it should be actually root 3 over 2. I think it should be root 3 over 2. Let me just make sure. Yeah, it's root 3 over 2. And that's because from the method before, how we said we're going from 1 to or 4 over 4 to 3 over 4, and then we were taking the square root of that, which is square root of 3 over 2. And then we go all the way back down. this is square root of 3 over 2, which is, just say 7.5 square root of 3. Give it in the exact answer, meters per second. And the velocity in the y is the hypotenuse of 15, which in this case the hypotenuse is like the actual velocity of the ball, times sine of 30 degrees. And this would be 15 times 1/2. And this would be 7.5 meters per second. And the important part of finding these values is because what we say in these kinematics problems is that the x and y components have no effect on each other. So we can break down this velocity into its individual x and y components, and then from that we can see that it has no effect on each other. And so essentially, really what we'd see is that, okay, if we treat this as a ball flying up at 7.5 meters per second, we'd be able to figure out, okay, how long would that be in the air, fighting against gravity before it hits the floor. And then once we figure out how much air time it has, then we can see that, okay, there's really nothing, like gravity isn't going sideways, and so this sideways x component is just going to remain constant for the entire time that the ball is in the air, if we neglect air resistance, if we don't account for air resistance at all, and then we can see from that then how far the ball goes. So if we say if from this, I guess just little tidbits for anyone who's curious, if we say from this that we say that, oh, the ball's in the air for 5 seconds, then from here we say, okay, if the ball is in the air for 5 seconds by looking at the y component, then we look at the x component and we say, okay, so that means it's traveling in the x direction, it's traveling to the right, 7.5 times root 3 meters per second, and it's traveling like that for 5 seconds. And so, oops, this should be an S. And so by multiplying these two values, we'd get that this is 37.5 times square root of 3 meters total that the ball traveled. And so this distance here, this distance, in which we'll call d, is equal to 37.5 times square root of 3 meters. And that is that very, very, I guess, detailed getting into this application. This is really only for people who want to see it, or are curious to kind of see this further application into the math, into the physics, because things being applied into other math concepts, like going from the unit circle into trigonometry, it still, at least for me, it remains too abstract. But then when you go from math into physics and other sciences, it starts to make a lot more sense, kind of why these things exist and what they're used for. But if you could not understand everything kind of below this line in terms of this application, that's completely fine. This is really just an extra, a bit of extra notes or extra detail for those who really want to see it. But yeah, I hope that this helps. Let me know if you have any questions about any of this in the comments below. And yeah, thanks for watching.